that everybody, I'm assuming you got the emails, but if not, it's worth me pointing this out. So today is going to be our last in-person class. I'm assuming, again, I don't know. I don't want to force you to come in tomorrow. Who knows what your traveling situation is and all that. I don't know. Because you guys you got the email. We're not in person next week. So I don't know whatever. So today is our last in-person class, first and foremost, and there will be no class tomorrow. Now I'm going to put materials up, but I'm not going to have a traditional class at 11 o'clock. So I'm going to put a video up. You guys watch it at your own leisure. And then we'll have a virtual class Tuesday. Hopefully you can make it. If not, no biggie. I won't be mad. Is everybody okay with this? Now, if you really want to be in person tomorrow, then send me an email and I'll truck up here and I'll be in person. But I'm assuming with everything that's happening, I don't want to put extra, and maybe it's not extra undue stress or whatever, but I just figured who the hell knows what's going on with you guys. So I'm going to put something up and then hopefully we can meet again on Tuesday. And then after Thanksgiving is finals week, I will have lots of available time for you to ask any questions about any homework. If you want to meet virtually, I'd be happy to do that. All that fun stuff. So I'll be putting some messages up on Canvas, and then our final is scheduled as we talked about before. So does anybody have a comment or question while I prepare my chemicals? Everybody doing all right with like the semester and everything? Like, what do you guys prefer? Would you prefer that you could be in person? I don't know. Like, what is the vibe? I think it's like a double-edged sword, because I think really you kind of want to be in person. But then when you're not in person, you have the option of not showing up, which is nice. And then you start convincing yourself that it's easier to not show up, right? I don't know. I think that's just a human nature thing, maybe. That's just my theory, because as the semester has gone on, the in-person people have slowly declined, right? And I notice everybody's still kind of logging on to Zoom in my classes. Not this one, but the other ones. But I don't even know if they're paying attention. Yeah.
There's my one class. The last class we had last week was the only in-person class.
Yeah, it's weird. And I would normally say you get an award, not an award, but I just don't know what kind of situation people are dealing with. So I feel bad. Like, if I have no idea they're like, well, you can watch into your dorms. But if you're in a dorm, you might have roommates, right? Or even an apartment, or who knows what the hell I can't even work from home. My house is like chaos. My kids are tearing the house upstairs down, it's like, it is a very difficult time. So, again, I feel bad because I'm trying to make it is less, the least amount of stress as possible for you guys. But the fact of the matter is, this is one class where we got a couple things going against us. One, it's a 4-credit class. So the amount of work is supposed to be more, right, than a 3-credit class. Also, this is calculus. So by default, there's a lot of work, and it just also happens that it's difficult work. So it's very overwhelming, particularly at the end of the semester. What I will tell you is, and this is not to knock other places or whatever, but I strongly feel that the way I give you guys exams is a lot more fair and stressless than, if you were at a big university right now, you'd be SHITTing yourself, because you're going to have to sit in front of a computer and take a 2.5-hour long calculus exam that's damn near impossible. That's the way it is, and I'm trying not to do that, because I don't think that's a good learning environment to begin with. So even when you get these homeworks, I posted a homework last night. It's long, it's difficult. We're going to talk about how to do it today, but this stuff is just difficult by nature. So it's not like, oh, Grady's the bad guy and he's trying to torture you. It's really, there's no easy way to give homework in this class. There's no easy way to give exams. It's difficult stuff. All right. That said, on Tuesday, we discussed area for regions in the plane whose, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, 118, 119, 120 boundary. I'm going to squeeze this in here. At least part of it is a continuous function. So that's kind of generic. And on the next page, I'll draw a picture just to remind you what we're talking about. So if we have an XY axis, which I'm just going to sketch briefly, and suppose I have a curve, and what we're going to do is we're going to assume that this curve is non-negative. So what that means is whatever function I have, I'm going to call it y equals f of x. We are assuming for this particular scenario that it never goes below the x-axis. And so what that means in symbols, this means the graph is above the x-axis. That's what that greater than or equal to means. And then if I pick any 2 points, I'll call one A, I'll call the other B. It doesn't matter if they're positive or negative. I'll just draw them. In the first quadrant. So the area of the red region is what we're trying to figure out. And so what we did, the idea was to start by approximating with rectangles. From above and below. Now, again, I drew a couple pictures of that. We went to that website and we tried to get you to visualize it. And again, I don't want to go into the details of this because we can't spend too much time on it. So if you want to get a deeper understanding of these ideas, what you need to do is think about this sentence and look at the pictures and what we did last class. We did it on a specific problem. We did it on the area under a parabola. And I would highly encourage you to study that. I put it on the homework so you can do it again yourself, or at least copy it out of your notes. It's an important idea because this what we're doing here with area, as we're going to see shortly, is not just something we can do for area. It turns out we can do it for all kinds of things. So maybe you've taken a physics class and you've heard of work before. Maybe you haven't. Maybe you've taken a physics class and heard of pressure or force. These are all things that we are going to be able to do these ideas on. And we'll do some of them in Calc 2 for those of you who take Calc 2. Even though you said you're not, I should force you. Say you're getting an F unless you take Calc 2. No, I'm just kidding. I should do that. Yeah, you see, that would get anybody to take it. It's a hard class, but it's rewarding because it shows people, hey, look at this person. They took Calc 2. Brave. So anyhow, think about this sentence. And so what we did is we approximated with these rectangles, and we created them in a very creative way. And what was awesome about this is we noticed some type of limit occurring. Now, of course, I'm writing that we noticed this. I was trying to illustrate this last class. I don't know if it was lost on you or not. So hopefully, if it was lost on you, what you can do is you can go back to the notes. And I guess I should spell occurring correctly. It's 2 R's. And so this limit turns out to be super useful, not just for area. So again, I can't emphasize this enough. This thing that we created last class, it can be interpreted as area, but it can be interpreted as much, much more. And so we're going to give it a name because of that. So what we're going to do is we're going to make a general definition, and this definition is called the Riemann integral, or integral for short. And its construction is based off of this idea of taking rectangles and then adding more and more rectangles. And what naturally happens is if I have a fixed space and I continue to add more and more rectangles, what must happen is their widths must get smaller and smaller. So as the number of rectangles keeps increasing and increasing and increasing, their widths must shrink. And so then if I have a curved region and I have rectangles inside, as we saw on that internet page on Tuesday, as I increase the number of rectangles, a couple hundred, a couple thousand, a couple million, those rectangles begin to look more and more like the shape itself. And I've alluded to these ideas before and forth. As I said, I've talked about movies, where I said, what is a movie? A movie is really just a bunch of pictures changing quickly so that your mind is believing things are moving. We can interpret any circle as really just a bunch of really, really small lines put together. Any curve, if you want, can be thought of as all these very small straight lines put together. This idea of taking something and chopping it up to small pieces is really what calculus is all about. We've been doing that since we talked about the tangent line and the derivative. Okay, so we motivated this thing called the derivative by asking questions about steepness of curves, and the physical interpretation of that is velocity. And so now we're introducing a new operation in calculus, which we're going to call the integral, and its motivation is this concept of area. So this limit is called the Riemann integral, or integral for short. And we'll be very specific. It's of f on the interval. So the interval was a comma b. So if you read this stuff in the book, they're going to motivate this slightly different than I am, and different books motivate it in a different way. It's actually a very difficult sort of idea, but we're going to give you the O'Grady version of it, which is true. It's just what I call a calculus 1 version of this definition. One that is the easiest to understand, in my opinion. So this is going to look scary, but what we want to do is we want to make a definition precise. So here's what we're going to do. On Tuesday, I drew a picture, and then I said, let's just pick. Remember, I put 4 points inside 0, 1, and I said, let's draw rectangles. And it might have seemed like, why was I picking those points? Well, there was a system to what I was doing. And so the idea is to construct rectangles in a way that it's easy to write down the pattern. That's the idea. So if I'm going to take the interval from A to B and chop it into pieces to build rectangles, maybe the best case thing I can do is let's just chop it into equal pieces. whether it's 4 equal or 8 or 100. And we want to be able to do it for any number of rectangles. So here's the scary part. So let n greater than or equal to 1 be an integer. So that means n is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, whatever, never. We're going to set delta x. So I'm going to use this notation. This is a triangle in front of the letter x. This is convention that you call this a triangle. Some people call this the Greek letter delta. And so this is delta x, and it's a number, and this is going to be the width of our rectangles. So if I want all my rectangles to be the same width, I'm going to take the length of my interval, which is b minus a, that's the length of it, and I'm going to divide it by how many rectangles I want. So yesterday, think about this. The problem we had, our interval was 0, 1, and I started with 4 rectangles. So if I apply this here, 1 minus 0 is 1, 1 over 4 is a fourth. So that's why it was 1/4, 2/4, and 3/4. Okay, great. Now, this is going to be real scary, so don't get upset. For each integer I, where I is greater than or equal to 0 and less than or equal to n, define x sub I as a plus I times delta x. Now, this is a scary definition, but again, when we apply this to a specific case, you'll see that this turns out to be, just like we did on Tuesday, this would be 1/4, 1/2, 3/4, and 1. So if you want to see the first few of these, look what they are. What's x sub 0? X sub 0 is a. X sub 1 becomes a plus delta x. X sub 2 becomes a plus 2 delta x. And this pattern goes on and on and on. And if you get all the way up to the nth one, what you're left with is a plus n delta x, but that simplifies to just b. So you might need to do some algebra to convince yourself of that. But what we're going to do in a moment is we're going to do this again for a very simple case of 0, 1. All right. And it's not, hopefully with one example, you see what's happening here. Do you guys have any comments of these questions? And it's very confusing. What you're seeing right now is confusing. It takes some time to understand this. Now, if you think about what I'm doing here, these points, we call these guys a partition. What these guys are going to do is they're going to break the interval AB. These are going to be the points where I construct my rectangle. So the first point is we start at A. And so if you think about it, if I draw a number line, and this is A and this is B, well then here is x sub 1, here is x sub 2, here is x sub 3, etc. And then this process goes on and on. And the idea is that each one of these is separated by a distance of delta x. So I'm setting up for the basis of my rectangles is what I'm doing. And by the way, don't forget that we call a sub 0 is another name for A, and x sub n is another name for B. Now, what we're going to do is we're going to take a limit. Does anybody have anything they want to say about this other than it's scary and I'm confused? I mean, you're allowed to be scared and confused. That's normal. It is. What do they say? I empathize and sympathize. I feel bad, not only because I know how hard it is, but I also feel bad because I just feel bad. All right. So very good. Now we get to make our definition. So if, well, let's do this way. So a better way of saying it. The sum. Now, let's look at this. What I'm going to do is I'm going to say f of x sub 1 times delta x plus f evaluated at x sub 2 times delta x. This sum, which goes all the way up, here's going to scare the hell out of you. This sum right here, which we can write. By the way, before I say anything, this looks overwhelming, but what are these things? This is the height and width of each rectangle. This is the height of the first rectangle. This is the width. Height of the second rectangle, the width. So this guy is called a Riemann sum. Notice it's not called the Riemann sum, it's called A, because this is a special type. In particular, it's called now, if you hearken back to our example on Tuesday, it's called a right Riemann sum because we were using the right end of each endpoint for our height. So a thing that's useful to note is two things. First, we can factor out the delta x. And so if you do that, you're left with convention to write it like this. I'm going to shorten it. So I'll factor the delta x out. And what I'd like you to note is that you can do that. And then I'd also like you to note that f evaluated at x sub I, I'm just going to use generic I. So I know this is sort of, well, I'll go 1 first. So f evaluated at x sub 1 is the height of the first rectangle. Delta x is the width. And so I would also put under there, etc., because f evaluated at x sub 2 is the height of the second. So for example, this is the height, this is the width of the second rectangle. Height, width. So even though this notation is very overwhelming, It's overwhelming only because it's that we have to define these things in general. Right? I don't know what F is. I don't know what N is. How many rectangles do I want? Do I want 10? Do I want 100? Do I want 1,000? Don't forget, the goal is to take a limit. And so that's why we're talking about an arbitrary number of rectangles. And that's a difficult concept to sort of get to the bottom of when you're a peasant in Calc 1. Okay, so here's the cool thing. And before I change pages, anybody have a comment, question? All right. Fact. If F is continuous on A comma B, then this limit exists. Doesn't mean it's easy to compute. But it does exist. Theory tells us that it exists. And if you're interested in why that's true, you take advanced math classes. Okay, so we denote this limit by the following notation. We write this elongated S, and then we put an A downstairs, we put a B upstairs, we put F of X, and then the letter dx. All kinds of scary things. So this is an elongated S. And it's called an integral sign. F of X is called the integrand. And the dx is called a differential. Now, that doesn't mean anything to you right now, other than you could think of it as like a grouping symbol. So when I say grouping symbol, you can think about this is a mathematical operation, like a derivative's an operation, or just like adding and subtracting are operations. So with this, you have this is on the left-hand side, and then you have this on the right-hand side. And what's happening is this is telling you how you're going to do something. You're going to do something to the function f, and one way to think about this differential right now is it's telling you what variable you're using. So the variable is irrelevant. Just like, you know, if I told you the function y equals x squared, or if I told you the function y equals t squared, is there any difference in those rules? No. The letter, if I said y equals cat squared, it's the same thing. So maybe you guys don't appreciate that. I don't know if I did. Sometimes I got to put my time machine in my head and say, did I know anything when I was in Calc 1? And the answer is no. I knew nothing. So a couple more remarks that should be stated before we go and do some examples. Number one, the notation is overwhelming. It takes time to learn. Or more importantly, it takes time to be comfortable with it. That's a poor sentence, but I don't care. It sounds good. The second remark is the variable is called a dummy variable. That's sort of the lingo. We shouldn't say that, but it is what it is. And so what I mean by that is the integral from a to b of f of x dx is the same thing as the integral from a to b of f of y dy, which is the same thing as the integral from a to b of f of star d star, which is the same thing as the integral from a to b of f of t dt, etc. I hope you understand the point. And on the homework, I try to beat that in your head by using different letters other than x. We don't always use x. In fact, in science classes and in applications, we often use t for the independent variable because that's usually referring to time. What's happening to the stalk? What's happening to the bacteria culture? What's this chemical reaction? What's the height of the plane? So we have a couple more remarks. Does anybody have anything they want to say? Does anybody have fun plans? Will you listen to the authorities and see nobody over Thanksgiving, or will you say, F the authorities, I am doing what I want. I'm going to party with friends and family. You don't have to tell me what you're going to do. I don't even care. Right? I don't know. I'm not going to snitch on you. I'm not kidding. My family literally had a Zoom meeting last night to discuss if we should get together for Thanksgiving. I said, what in the hell world am I living in right now? And I say that as a snowflake. Whatever that means. Isn't that what they call people, the liberal snowflakes? Ain't that what, like, Fox News calls them and stuff like that? You guys watch the news or anything? Or what? I wouldn't even call it news. Do you watch TV? No? What do you watch? Netflix or what?
I only watch TV for sports.
Right. Okay. Yeah. Me too. Yet I have a $300 cable bill because some strange reason my wife refuses to get rid of it. I literally watch it for sports, and then sometimes we watch some things on Netflix, I guess. Amy's watching this show called Emily in Paris. It looks awful. I cringe when it's on. Do you guys ever watch that show? Do you know who that is? What do you guys watch? Yeah, I watch this other show with her called Younger. Holy hell. I mean, easy. Here I go, insensitive and sexist. It's a chick show, right? That's what it is. I'm going to get fined for these comments. I kid. I don't know. What else you call? All right, here's our third remark. And sort of this is going to lead us into the next sort of idea. These limits are difficult to compute unless there is a simple, and I'll put simple in quotations, pattern. So like last class, we saw there was a simple pattern. So for example, there are two simple patterns. Or here are, here are a couple, let's say a couple. So here are a few. For example, if I take the number 1 plus the number 1 plus the number 1, if I want to add the number 1 together, let's say n times, what is this equal to? Well, when you were a kid, you learned that 1 plus 1 plus 1 plus 1 plus 1 n times is equal to n, right? If I add 1 up 4 times, I get 1 plus 1 plus 1 plus 1, which is 4. If I add up 1 32 times, I get 32. So this is a simple pattern. You should know this. The next one is not as obvious, but we can show you where it comes from in a second. You can add up 1 plus 2 plus 3 plus 4. And if you go all the way up to some number n, this has a simple formula. It's n times the integer that comes after n all over 2. And then lastly, the one we talked about on Tuesday is that if I want to square each integer and add them up, then there's also a pattern. It's n times n plus 1 times 2n plus 1 all over 6. Now, I'm not saying you have to memorize these because you don't. I'm not going to test you on them, but these are very useful patterns that you should be familiar with. So, any questions about this? This one, number 2, is not difficult to actually verify yourself. It's not hard. You can just do some creative algebra. The third one is not, you need some more advanced techniques. But as I told you on Tuesday, you could convince yourself these are true. Just pick some small values of n. Like, for example, when n is 4, what is 1 plus 2 plus 3 plus 4? Well, that's 10, right? 3 and 4 is 7. 7 and 3 is 10. Now replace n with 4. What's 4 times 5? 20. What's 20 divided by 2? 10. So you can verify that it's true. We're not going to ask you to prove it, though. Now here's something that's going to drive you nuts. And this is our 4th remark. And you're only going to learn this if you spend time doing it. The 4th remark is we need better notation. For what we say as long sums. So one of the things you're going to have to get comfortable with is a new notation that we use pretty much from this point forward. And it's difficult to learn at first. It's confusing. And it's called sigma notation or summation notation. So let's take so let a sub 1, a sub 2, a sub 3, etc., all the way up to, say, a sub n. Let these guys be a list of numbers. That we want to add. So we write a sub 1 plus a sub 2 plus a sub 3 all the way up to the nth one. Instead of writing this big thing, we compact it and we write this. So this thing reads for sum. So when you see in a math class or a physics class or maybe in a statistics class, if any of you taken prob and stats, usually in a stats book when they talk about the mean or the average, they use this notation. This means sum. So this is the Greek letter sigma. So what we'll do is we'll take the three sums from the previous page and we're going to write them in this notation. You have to get comfortable with this. And it's not easy. It sucks. It's like being a kid having to get shots. It sucks. No one likes it at first. Nobody does. It's confusing. It doesn't look good. It's aesthetically non-pleasing. But guess what? When you become you're more familiar with it, you realize it's useful. It's a shortcut notation. It just compacts. All right. So does anybody have a question about this? All right. So let's look at some examples of this. So for example, if I have 1 plus 1 plus 1 plus 1, and I want to do this, say, I don't know, let's say for the heck of it, let's say, what's today's date? The 19th, 19 copies. If I want to write this in a shorthand notation, I might write this as the sum k goes from 1 to 19, and I'll put a 1 here because each one of these numbers is 1. Say we want to add the numbers all the way up to 23. We might write the sum k goes from 1 to 23. This time I'm going to write k because it changes at each step in the sum. So this is the first piece where we're going to start to get a little sort of overwhelmed. And then lastly, we'll do this one. Let's say this is 12 squared. Then this becomes the sum. K goes from 1 to 12 of k squared. Comments, questions? Now we're going to write one more thing, then we're going to do some examples. That's exciting. This is overwhelming, right? The good news is all this, it's kind of funny because all this is sort of for naught. And the reason we say that is computing these integrals from the definition is really challenging. And I alluded to that Tuesday when we talked about area in general. But tomorrow, whenever you watch the video, that we would normally do tomorrow, we're going to show you a sort of shortcut that works. And it's really not a shortcut in the sense that we couldn't use it as the definition. It's a shortcut in the sense that it's a pretty powerful theorem. It's going to take this ridiculous amount of computation and change it into a very simple operation. But we have to have an appreciation for that, and that's why we do some of these the long way. Just like with the derivative, what was the definition of the derivative? It was a scary limit, right? Limit as h goes to 0 of blah minus blah over h, and that's complicated and difficult. And what you do is you develop shortcuts and rules for computing derivatives. It doesn't always work, but it works on lots of situations. And we're going to do a similar thing here. All right, so the last thing I want to say is we can now rewrite our definition. So we can rewrite the definition of the definite or Riemann integral. Oh, that's another sort of synonym for this, the definite or Riemann integral. The integral from a to b of f of x dx is equal to, here we go, the limit as n goes to infinity of the sum as, say, I goes from 1 to n of f evaluated at x sub I times delta x. And don't forget, I'll write it down again just so you're here. Delta x is b minus a over n. X sub I is a plus I delta x. Yikes. Now, the good and the bad of this is this looks scary, especially this right-hand side. But the right-hand side is important to remember because the right-hand side is what allows you to apply these ideas to all kinds of applications, not just area, but volumes, to forces, to pressures, to all kinds of different things, and not just the physical sciences, but in the social sciences and finance and economics. I'm not making this crap up, I promise you. All right. Whew. Now, notice that in this definition, I didn't say anything about f being positive right now. This makes sense for any f as long as it's continuous. Now, we can, in certain cases, interpret this as area, but this is bigger than just area. Area is one thing we can answer with this. It's not the only thing. Do we understand that? Just like velocity is one thing we can get from the derivative, but it's not the only thing we can get from the derivative. Under the correct interpretation, you can think of this number. By the way, this is a number. This is going to be a number because this limit is a number. So here's what we showed last class, even though we didn't say that we showed it, but this is what we showed. So last class, what we did is we showed that the integral from 0 to 1 of x squared dx, we showed that it was equal to 1/3. That's what we showed. And so we can interpret this as an area. So the operative word is we can. Not that we have to, that we can. So if I draw this, it's useful when you're learning this integral to think about the geometric interpretation. And one of the geometric interpretations is that it's the area. So if I draw the curve, my parabola. So what I'm saying is this integral so by the way, this is the point 1, 1. So the area of the red region is 1/3. And just so that it's ultimately clear, this is the curve y equals x squared. And I'm restricting myself between 0 and 1. Any comments, questions? Now, we constructed it. When I did that construction on Tuesday, I didn't tell you anything about an integral, but that's exactly what I did. So we're going to do another one right now so you can see how it works. And then it will help you with your homework. Comments, questions? Okay, so let's do another example. Let's integrate from 0 to 1 the function x dx. So what is this equal to? So we're going to do a few things. The first thing we want to do is I want to draw the picture. Then I want to approximate the integral with n equals 4, 10, and then 100 rectangles. It sounds overwhelming, but it's going to be pretty easy. And then the last thing I want to do is I want to compute the exact value. So this is sort of what I'm asking you to do on the homework. Is anybody curious or have a comment, question about what I'm asking to do here or what I want to do? All right, so let's draw the picture. So I'm going to use some common sense. I know I'm only interested in, the function I'm interested in is f of x equals x. and I'm interested from 0 to 1. So if I draw this line, looks like this. I guess I should, this is the number 1. Guess I should make this go a little further. Okay, so this point right here on the curve is 1, 1. And the integral that I'm after is, what it's doing is it's going to tell me the area of this region, which happens to be a triangle. So if our definition of the integral is useful to us as an area, then we know what we should be getting here at the end of the day. We better get that the integral is what? Well, the area of this triangle is 1/2 the base times the height, so we better get that this area is 1/2. So that's the picture. So the red triangle area is equal to this. And which, of course, we better get 1/2, right? Or we did something wrong, or this is a bad definition. Do you understand the point I'm making there? So that's sort of the picture. Let's now look at setting this thing up. So by definition, delta x is 1 minus 0 over n, which of course is 1 over n. And what are our x sub i's? Our x sub i's are 0 plus I delta x. But of course, that's going to simplify. That's going to be I times 1 over n, which we can just write as I over n. So look, the best thing we can do right away is we can jump into, let's just to help your mind understand what's happening. Let's look at the case when n equals 4 right away. When n equals 4, delta x is 1/4. X sub 1 is 1/4. X sub 2 is 2/4. X sub 3 is 3/4. And x sub 4 is 4/4. And if I draw the number line from 0 to 1, those are exactly the points that if I break it into 4 equal pieces. Now, if I used n equals 10 or 100, I mean, 100's too many to draw, but you could probably draw 10 if you wanted to. But I'm going to use 4 just to illustrate it. So the thing is this, like, if you look over here, this notation is very overwhelming. There's so many letters floating around. But look, there's a connection. There's patterns here. Here, I represents, we call this an index. And it's tough to learn this, but that's just, you know, again, you have to read the book. You have to think of the context here. Another thing to think about is that each one of these, you know, the distance between all of these is 1/4, which is of course the same as delta x, because I'm in the case n equals 4. so let's finish this up real quick. We're running out of time. So here's what we know. So the Riemann sum is, let's write it out in general. It's f of x sub I goes from 1 to n, times delta x. Now, this looks scary, but remember, this is shorthand for the following. It's shorthand for f evaluated at x sub 1 plus f evaluated at x sub 2, all the way up to the nth value. And then, of course, this is times delta x. Now, we know what f is, and we know what the x sub 1 and x sub 2 are. This becomes, what is f? Well, f is just the function. So it's the function f of x equals x. So it spits out its input. So the input here is x sub 1 plus x sub 2 plus x sub 3, all the way up to x sub n. And what is delta x? We already know what that is. It's 1 over n. Now we know what each one of these values are. What is x sub 1? Well, we know what it is. It's 1 over n. What is x sub 2? 2 over n. What is x sub 3? 3 over n. And of course, this goes all the way up to n over n. And what I'm going to do now is I'm going to do exactly what I did on Tuesday. I am going to factor something out. In particular, I can factor out an n from the denominator. So I'm going to rewrite this. I'm going to pull the 1n out front. So this becomes 1 over n squared. And what's left is 1 plus 2 plus 3 all the way up to n. And then I told you a few pages back that we have a little formula for this sum. This sum becomes 1 over n squared, and this becomes n times n plus 1 over 2. And if I just do some algebra, I'm left with n squared plus n over 2n squared. So there's a lot happening here. Let's not pretend there isn't. There's an awful lot happening. You ain't learning this in 5 minutes. You just aren't. This is something that you're going to have to spend some time on if you want to have a better understanding of it. So real quickly, what I'd like to do is in a minute, we can finish this problem. But does anybody want to say anything? Yeah. Is it the direct opposite of it? Not sort of, but this has nothing to do with derivatives yet, right? So yeah, what we're going to talk about next is the fact that the derivative, look, all this is difficult, right? We're going to find is we don't have to do it the difficult way if we understand that it is the opposite of differentiation. So as I said, we're going to see tomorrow that there is a way to do this in with 1 or 2 mathematical operations. It's not going to take all this. But why is it important that we do it this way in the beginning? It's important this way because this is the idea. The idea of what's happening is almost more important than actually computing these things. Because what we're going to find is we have software to do these things for us now. And so in the real world, when we want to use calculus, it's not so much that we get the value of the integral. It's that we understand when to use an integral and what it represents. Do you understand what I mean by that? So when we take calculus 2 and we take physics and we take other classes that use mathematics as a tool, we have to understand that the most important thing about the integral is how it's constructed and what information that can give us. We saw it can already give us area. All right, so here's what we have. Real briefly, we have the following. So for n, equals 4, we get the integral from 0 to 1 of x dx is approximately 4 squared. Look at our formula from the previous page. It's n squared plus n over 2n squared plus 4 over 2 times 4 squared. So if you just take out a calculator real quick, and if you want to leave, you're not going to offend me, but I want to knock this out. It'll take less than a minute. So you have, I mean, what is this? It's 16 plus 4, which is 20 over 32, right? So you can write this as 20 over 32, which is equal to 0.625. Okay, not very good approximation. What about when n is equal to 10? When n is equal to 10, you get 10 squared over 10 all over 2 times 10 squared, which of course is 110 over 200. And of course, if you go to a calculator, you get 0.55. And then for n equals 100, you get 100 squared plus 100 over 2 times 100 squared. So that gives you what? 10,000 or 10,100 over 20,000. What you get 5.05. So what the idea is that, oh, I forgot a 0 in that. What? Oh, wrong button. Oh my God, I'm losing my mind. So you get 0.505. And so the idea is that we see that as n gets larger, it looks like there's a limit happening. And so lastly, if we take the limit, this integral, which is the area of the triangle on the previous page, this integral is this limit. Now, remember, back in chapter 2, we took limits like this. And these limits at infinity, you can use L'Hopital if you want, or you can just say, look at the degrees. The degree here is 2, the degree here is 2, so you look at the leading coefficients, and it's 1. Bingo. Now, that's a lot, and we took over time, and I apologize, but I think it's important that you have this if you want to learn it tonight or tomorrow or whenever. So thank you, guys. Hopefully you'll ask questions or whatever. And if there's anything I can do, let me know. This is difficult, so good luck. And let me know. And like I said, we'll meet together next Thursday. I'll post some stuff on Canvas for you. If you need to Zoom at all and ask questions, please. I know you emailed me about talking, and I don't know if any of you did recently, but I'm happy to do it. So I'll get back to you hopefully tonight or tomorrow morning. And in all finals week, I'll be there. So, all right, guys, thank you very much. Good luck and be safe. Take care. Is this going to work for me? Good. And now on to the next one.